So welcome back. Example number 3 from chapter 12. We have a scenario where a market research firm wishes to study the relationship between wine consumption and whether a person likes to watch professional tennis. 100 randomly selected people are asked whether they drink wine and whether they watch tennis, and the following results are obtained. So I hope you all recognize that this is a contingency table, much like we've seen and used in chapter 4 for probabilities. Question goes on to ask you to calculate the corresponding row and column percentages as well as cell percentages. It's a very silly question because clearly you can see that 16 out of 100 people equates to 16%. So the first two parts of the problem are pretty simple, straightforward. Part C is where it's important. It says test the hypothesis, so already you know what you need to do. That whether people drink wine is independent of people who watch tennis. So the key word here is independent. Immediately this is a strong signal that says this is a chi-squared test for independence. And they tell us to set alpha equal to 5%. And part D simply says, given the results, does it make sense to advertise wine during televised tennis matches? So what can we do with the result? As usual, we start off with step number 1, which is state the hypothesis. Because I have terrible handwriting, I've already typed it out. HO, wine drinking is independent of watching tennis on TV. Always, always, always state the null hypothesis as independent and the alternative as not independent. Never say dependent. So HO, wine drinking is independent from watching tennis on TV. HA, wine drinking is not independent of watching tennis on TV. Number 2, we need a critical value. The critical value will also be chi-squared, as we've learned. We know that alpha is going to be 5%, and we need a value for degrees of freedom. So when you have a contingency table or a test of independence, the degrees of freedom are calculated as row minus 1, column minus 1. And in this particular case, it's a 2 by 2. If you don't believe me, here it is. So we've got 2 rows, 2 columns. We don't count the total. So for this, it's going to be 2 minus 1 times 2 minus 1, which is equal to 1. Okay, so we're going to have a degree of freedom equal to 1. What is that? We go to the chi-squared table. We need 5% in the tail. We take this column and we take the first row. Which gives us 3.84. So we know it's 3.84. Clean it up here. For illustrative purposes, let's go ahead and add the chi-squared right there. And here is your cutoff mark. Of course, any test statistic that comes in to the right, reject HO. Anything that comes in to the left, do not reject HO. So, step 3, the test statistic is going to be chi-squared star is going to be equal to the sum of observed IJ minus expected IJ squared divided by expected IJ. I means ith column, and j is the jth row. Or either or, it doesn't really matter. So essentially they're telling you to sum up the difference between expected and observed for each one of these 4 observations. So this is row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. Okay? So the only piece of information you don't have right now are the expectations. You don't have these guys. Very easy to calculate them. So I'm going to go ahead and redraw the table here this way. What you want to do, very similar to what you did in probabilities, is you need to take the column total, multiply it by the row total, and then divide by the total. So in this particular case, 20 times 40 divided by 100 should give you 8, which stands for 8%. So I'm going to go ahead and write it in green. And so here it would be 8. So this is your expected. This is your observed. Doing the same thing for the rest of them. We have 12, then you have 32, and then you have 48. Once that's done, the math is pretty easy. Step 1, 16. Let's use a different color pen. 16 minus 8 squared divided by 8 plus 24 minus 32 squared divided by 32 plus 4 minus 12 squared over 12. 56 minus 48 squared divided by 48. 16.67. I rounded. Take that, place it on the distribution. And so now you know what the conclusion is. Number 4. We reject HO. What are we rejecting? We are rejecting that they are independent of each other.